already recording
Uh, Maybe it is already
currently?
recording. All right, who knows? Uh, anyway, so as you know, Gary Bernstein has agreed to talk with us today. As you'll hear, his algorithm for and software for the dark energy camera astrometry was very successful, and I think it's basically been adopted as part of the LSST pipeline. He warned that he's not here to report on actual LSST performance, so we will have to bother other people for that. But why don't you just take it away and tell us whatever you'd like.
Okay, let's see. Can you turn on the sharing for
Oh,
me?
I'm sorry. Uh, uh, One moment.
Okay, I'll say in advance, I don't know my audience here very well, so uh, if I'm talking about things that are already well known or uh, uh, talking
It should
about things
work
that
now,
don't,
I hope.
okay, um, do interrupt me. Let's see. So here are slides, I think. Yeah, you can see those. Okay.
I can see
Okay,
it.
so I want to let you all know about something I hope will be end up being very useful to you. That is involves both DCAM and LSST. So I'm the one giving the talk, but the project I'm going to describe that is trying to, as we say, jumpstart LSST with DCAM data. That has people working on it here at Penn, which is me and two students, Vernon Wetzel and Daniel Gomez. And then at Chicago slash Fermilab, there's Alex Derlicka Wagner and Chinyi Tan. And I should say that none of those people are actually doing the astrometry on Rubin. That is the domain right now of Claire Saunders and Pierre Francois Leger, who I have a couple of slides from about how things are going with the very early data. But they're the ones who are going to be doing the implementing at that end. So I won't try to take credit for it. Okay, so the outline here is that I'll just talk generally about doing precision astrometry from ground-based surveys and report on what we did for the dark energy survey that worked pretty well in improving both what we'll call the static solution and the stochastic or atmospheric turbulence part, and I'll get back to what those are in a moment. Then I'll describe our project to re-reduce all 12 years of DCAM images. I think it's hundreds of thousands of sky exposures that have been taken to try to get good astrometry and reduce them all to proper motion and parallax catalogs, and then talk about what happens when you add those to LSST data that would be forthcoming. Okay, so just to set the scale, the whole field of view of the LSST camera is about 12 million milliarc seconds, right? To put it in a strange way, one pixel is about 300 milliarc seconds. Sorry, the PSF, the sigma of it, is about 300 milliarc seconds. Hopefully, will be once the camera's all focused and everything. A single pixel is about 200 milliarc seconds, and the requirement or design spec and goal for how well they can do astrometry in a single epoch are 20, 10, and 5 milliarc seconds, respectively. And I'll show you that we actually do something around 3 milliarc seconds with the DCAM, in particular with the dark energy survey data. So, in other words, LSST should be much better than the design and should easily exceed its goal. All right. And just for scale, a single silicon atom is 11 microarc seconds. So we're actually looking for shifts that are a few hundred atoms. Okay. So just to put that in terms that I guess are relevant for you guys, I don't know what you define solar neighborhood is. How far away am I allowed to go and still be in the solar neighborhood? But if it's 100 parsecs, then That's a 10 milliarc second, right? Parallax. And if there's a Jupiter around one of those stars, it's a half a milliarc second. So those are things that we should be able to do. Okay, so to go, the two main steps of astrometry, right, are going from, you can see my cursor, I hope, right? And going from the image, the X and Y pixel data, to a centroid in XY space, and then having a world coordinate system solution, which takes you from XY space to RA-DEC space. And we're going to split this second WCS part into what I might call the instrument or static map. That is to say, it's something that's predictable, at least over the course, hopefully, of hours to weeks. And then another stochastic, or what I'll call exposure part of the map, that goes from the tangent plane of the telescope bore out to the actual sky. Okay. We used to have a distinction between relative and absolute astrometric accuracy, but in the days of Gaia, DR2, DR3, we have plenty of Gaia accuracy stars to serve as the relative partners, which basically means relative and absolute have no more distinction, right? Okay. So just to talk briefly about the centroid part, where you actually want to get an X and a Y value for the centroid of the star, you can use a Kramer-Rao theorem or Fisher matrix to write down what the theoretical accuracy, best possible accuracy of the uncertainty on the X position should be as a function of what the noise level in the image and what the PSF and its derivatives look like. And it turns out that if you do a PSF fitting or a Gaussian weighted aperture centroiding, they can be equal to this bound in principle, and in practice get very close. Okay, so we can consider centroiding, I think, to be a essentially perfect process for the most part. And the rule of thumb is that the RMS error in the centroid, when you're done, will be about the RMS width of the PSF divided by the signal-to-noise ratio of your detection of that star. And if we look up what LSST should be doing, there's a point at around magnitude 20.7 where the noise from the sky background and the noise from the star are about equal. And at that point, if we take typical expected LSST performance, we expect at that magnitude the shot noise in the star, the noise in the stellar position to be about 3 milliarc seconds. Right? Brighter than that, things will get better, sort of as the inverse square root of the flux. And fainter than that, they'll get worse linearly with the flux of the star. Okay, so Gaia DR5 is supposed to give us at G of 20 about 0.4 milliarc seconds errors. So that means at G of 20, where Gaia stops giving us information, a single LSST visit should have shot noise that's only about 5 times worse than the whole Gaia mission. So since LSST is going to measure every star a lot more than 25 times, we expect LSST to do better than Gaia at Gaia's faint end. And of course, do all the stars fainter than that. Okay. So shot noise is looking pretty good for us. So now let's talk about world coordinate systems, right? A photon that heads to us from a star. What determines if that star is really at some alpha delta? What determines what X and Y pixel coordinates we measure for it? Well, it has to go through a whole bunch of hurdles, I guess, or distortions before it gets to us. And I've just listed them here. So there's gravitational deflection by things in the solar system. There's stellar aberration from the Earth's motion. There's refraction once you enter the atmosphere. And in fact, there's a wavelength-dependent part of that that's differential chromatic refraction, or DCR. And then on top of that, there's not just the static atmosphere, but there's turbulence in the atmosphere that causes a stochastic deflection pattern. Right? And then once the photons make it to the telescope, then there is some kind of distortion or optical pattern, right, that brings those photons to a certain location in the physical focal plane. And that can be wavelength dependent too if we've gone through refracting elements, which we will on LSST and DES. Then we have to know something about where the CCDs were oriented in the focal plane and which pixels they landed on the photons. And then but when they get turned into electrons, they actually keep getting deflected a little bit. If there's electric fields in the detector, they can move the electrons. And sometimes the pixels aren't a perfectly square grid either. So we basically have to undo all of these things to turn the XY back into an alpha delta, right? And I'm going to split it into the parts of this, basically everything other than number 4 that should stay the same or be predictable on a night-to-night basis, okay? And then we'll have this turbulence. Okay, so this might make your head explode trying to solve this, but we actually, for DECam, in particular for the dark energy survey, which is about 80,000 useful exposures, GRIZ ones, we did make a model that was able to, for the stochastic part, which seems to be accurate to a milliarc second or so, as measured by looking for temporally persistent correlated errors between stars. Okay. So this table from the paper that he wrote about 9 years ago now lists all of the specific distortion steps that are in that model. And at the right-hand column is the size of the correction that each of these ends up making. And you can see that if we want to get down to milliarc second accuracy, which we do, all of these are important to have a model for. And you end up with hundreds of parameters once you look at the whole 62 CCDs that make up DECam. And that might seem like a very tough thing to try to fit, but we have millions of constraints because every star that we image on the camera more than once, right, is a constraint that its sky position should be the same, or at least moving along a 5-parameter solution, right? And then that's even internal, that the internal consistency information is even stronger than the information of making sure that each individual exposure matches Gaia. So we wrote software that could do these solutions, and that software is being adapted and now used on Rubin data by Claire Saunders. Okay, so I'll just very quickly explain a few of these things and show you their signals if you're interested. The CCDs on DECam and on LSST, they have their individual pixels, but the pixels are about 10 to 15 microns across, but they're a couple of hundred microns deep. So for a blue photon, it enters from the bottom and turns into an electron here, but the electron has to get pulled all the way down to the gates on the so-called front side of the CCD. And if there are any electric fields that have a horizontal component, they will pull the photons on their journey from the backside to the front side. Okay. So these are long, skinny pixels, and that means that you see these things easily. And we can see a few reasons why there are these horizontal electric fields in the detector. The detector, a CCD, is basically a flat parallel plate capacitor. So it should be mostly vertical, but around the edges it's not. And the left-hand plot here shows you that we can see shifts occurring at the 20 to 30 milliarc second level in the 100-ish pixels that are closest to the edge of our CCDs. The LSST CCDs have something that fixes this, greatly reduces this problem. And then here's a flat field image from a typical CCD in DECam, and it shows these things that are called tree rings, and they turn out to be rings of growth of the silicon crystal that the CCD was cut out of, and the impurity level or the doping level changes very slightly as the crystal is grown, And it turns out that leaves behind remnant hole and fluctuations, impurities that create electric fields. And we can see that there are astrometric distortion patterns that follow those rings. Right? And so by looking at the flat field, we create a template that looks like the wiggly red line, and we subtract that from the photometry. We see residuals that look like the green line. So we've taken a 10 or 20 milliarc second residual and reduced it again to maybe a milliarc second or so. The next thing in the astrometric model, besides these stray electric fields, are optical effects. And for instance, there is lateral color. This shows the color-dependent distortion of stellar positions that we see in the G band. It's much weaker in the R band, and it's basically undetectable in IZY. This is what they look like as a function of radius for a 1 magnitude color shift. And the nice thing is that optics actually tells us this should happen, and it does happen, so great. Okay. The next thing that we have is that the CCDs, where are they in the focal plane? It turns out that they can move around a little bit, and they do move around, particularly when the camera is warmed up and cooled back down to its operating temperature. Here's an example of the shifts, greatly magnified, of course, that we saw during one warm-up and cool-down event. And just here's the one of the CCDs. This shows how it moved over the last 12 years. The vertical lines here are when there was some kind of camera event. Okay, so again, tens of milliarc seconds. And then there's differential chromatic refraction, which does scale with the tangent of the zenith angle as one would expect. Okay, and then even when we've done all those things and we average up the residuals, astrometric residuals of its chip, we can see something like that. And when you take the divergence and curl of that residual pattern, you see that it's curl-free, which means it probably comes from a potential, which is what electric fields do. And you see that there's this pattern in the potential, and this is what the connector on the back of the CCD looks like, right? So we can even see things like this that are at the milliarc second level. It's pretty cool. All right. Okay, so we have what we think is a static solution, for each night of observing that that's right to within a few milliarc seconds. But if you look at an individual exposure and look at the residuals to that, you see patterns like this. And every exposure is different. And if you take the divergence and curl of that, you see, again, it's a curl-free pattern. And that's almost certainly because of the index of refraction variations in the atmosphere. And if you take the gradient of those, you get a deflection pattern. And you can see it looks kind of streaky, and that's probably because this is the dominant wind direction above the telescope, so that over the course of an exposure, a given pattern of turbulence is being carried across the exposure. And so one thing is that this pattern is streaky like this, but it also means that these remnant deflections are anisotropic, that they also have a preferred direction. They vary more in the across turbulence direction than they do in the along turbulence direction. Okay, so what can we do about this? And oh, by the way, so here's a plot saying that typically in the DES exposures, we might see the major axis of the turbulence covariance matrix being 5 to 10 milliarc seconds, and the minor axis being more like 5. We can expect this to maybe be a little bit different in LSST. It has a bigger aperture, which averages more turbulence, and so that would reduce the size of the turbulence deflection. But they are using 30-second effective exposures instead of the 90-second that we did in DES, which means there's less time to average over the turbulence. So those two things will counteract each other, and maybe we'll end up with similar turbulence. Um, this 10-ish milliarc seconds RMS in DES in Rubin exposures as well. Okay, so the good news is that this turbulence, although it's like a 10 or so milliarc second disturbance, which depends a lot on the weather, and that means that for any stars down to 1 or 2 magnitudes brighter than Gaia's limit, this turbulence will be bigger than the shot noise of a single exposure. And that means we could gain by getting rid of this turbulence pattern somehow. And the good news is that the turbulence pattern has a coherence length of about 10 arc minutes, whereas there's about 1 Gaia star every arc minute. So we can use the Gaia stars to measure the turbulence on a given exposure. And a few years ago, I had an undergrad here who's now at Delaware with John Willow Fortino, who showed that you could use Gaussian process interpolation to figure out what the turbulence should be at any given location by interpolating between the measured turbulence on the Gaia stars. And that reduced the turbulence variance by about a factor of 10. So this is like having now 10 LSST exposures instead of 1, right? Which is a pretty good gain for basically $0 extra spent. And a current PhD student who's graduating this year, Daniel Gomez, has improved Willow's algorithm to make it robust and much faster so that it can be run successfully on every LSST exposure. And that's something that Pierre-François Léger is actually doing right now, is implementing that algorithm. Okay, so the next thing that's happening is that we're applying this improved algorithm to the entirety of DECam exposures. So Alex and Chinyi and their Delve collaborators, some of whom maybe you on the phone, I don't know, on the call here, but they've located basically another 150, 200,000 exposures that are good, that allow us to cover the entire southern footprint, and I'll show you that in a second. But Daniel has gone and run his turbulence algorithm on all 80,000 DES exposures. And this is a density plot here where the x-axis is the log base 10 of the variance of the turbulence deflection before on the x-axis, and after on the y-axis we interpolate from the Gaia stars. And so a 2 here means 10 squared or 100 milliarc seconds squared of variance. So the typical spot here has about 10 milliarc seconds of RMS of turbulence, which is reduced by a factor of root 10 to be about 3 milliarc seconds RMS. So this is what we can achieve now on DES exposures. And of course, there's good nights and bad nights for turbulence, just like there's good nights and bad nights for seeing and for clouds. But it seems like no matter what, this Gaia gives you a factor of 10 improvement, okay, roughly. Okay, and as I said, codes that do this on Rubin images are already running. All right. Now getting back to DECam, this is a figure from Chinyi and Alex and Delve, where it shows you when DECam first observed a given part on the sky with a useful exposure. And I think this red line is the northern limit of LSST. And you can see that essentially all of it has been covered by DECam up to what is going to be 13 years before the LSST actually begins, right? So for proper motions, that's a huge advantage. And these plots show that most of that sky area has an exposure that's before, say, 2019 or 2020, and has 10 to 20 exposures from DECam that cover it. So that means that we should be able to get a lot of information from this whole thing about proper motions. Parallax is a little dicier, right? Because DES, for example, took data usually during the same season, and when the fields were near opposition, and so we don't have much of a parallax baseline. It's not optimal for that, but we'll take what we get, right, and see what happens. And improving the proper motion will improve the parallax solutions anyway. Okay, so the Penn and Chicago groups, we got a grant from the NSF to do this project, which is titled Jumpstarting LSST or something. So the idea is to curate and reprocess all the useful DECam exposures for the 12, now 13 years before LSST begins, derive new astrometric solutions, get turbulence solutions for them and take that out, and then fit 5-parameter models to all the stars that have enough sufficient number of exposures, publish that catalog for people to use right away, and to be able to be ingested to Rubin for good proper motions from Rubin starting the first year. So there's one major algorithmic challenge here, which is finding high proper motion stars in data like DES or Rubin's. And the reason is that these high proper motion stars tend to fall between the cracks. There are 2 reduction pipelines in Rubin. One is for the moving objects, but the moving objects are defined as moving generally if motion can be seen over the course of a night or hours or maybe a day, right? And obviously even a high proper motion star is not going to show up as a difference image between 2 days. So we missed those. And then the other pipeline is the so-called static pipeline, and that's where people look for things on coads, say annual coads. But if you add together a high proper motion star on the coad, you'll usually get junk, right? Because either it will be discarded as being an outlier for appearing in one point on one exposure but not being there on another exposure, or you'll get some kind of smeared object in the coad. So they don't even register as stars, right, in the coad image. And this set of pictures here that Vernon Wetzel put together shows what the DES coads look like for a few of the high proper motion stars in Gaia. But on the upper plots here are the locations of those stars as recorded by a DES on individual exposures, and you can see that they're very nice fits to linear motion over time. So Vernon has written an algorithm that goes back to the single exposure catalogs for DES and tries to find all of the sets of stars that fit lines like this of motion across the sky, or any 5-parameter fit. Okay, so this is a rather intensive job to do, but we think we have a working algorithm, and Vernon is still working on it to try to reduce the false positive rate. But he has shown, doing some implantation experiments, that we can expect to get good proper motion data from DES down to about 24th GMAG, with very weak dependence on what the proper motion is, all the way from 0 up to a few arc seconds per year, sorry. I'm still thinking about trans-Neptunian objects. So that's good, right? That's what we'll be able to do. And with that data, this is a figure from our proposal, saying what proper motion uncertainty do you expect to get versus I-band magnitude. And the top graph is if you just have 1 year of LSST. The cyan line here is what we expect it to do from DECam, from a typical part of the sky. And you can see that with DECam, we actually should be able to actually do as good as Gaia DR3 near its faint limit and go, as you've seen, a few magnitudes fainter. But if you combine that LSST first year with DECam, you get down here to the purple line, which will pretty quickly after LSST begins and finishes its first year, right, will be as good as the expected DR5 results from Gaia at Gaia's faint limit, and of course going quite a few years, quite a bit later. And LSS quite a few magnitudes later. And LSST by itself would take 5 years to get to that accuracy. Right? So essentially, we hope to give everybody a 4-year head start on what you want to do with the stellar motions in LSST. And then after 10 years of LSST plus the extra 12 years of baseline that it gives, it should be down here, which is actually better than Gaia for 18th mag or fainter. Okay. So that's what we're trying to do. We can show you some initial results. This is what, for a few heel pixels worth of the DES footprint, this is what Vernon is getting for the DECam only proper motion uncertainties, which is pleasingly close to our prediction of what we would get. I should say that the rest of the southern hemisphere outside of DES's footprint has much less regular temporal coverage and not as many exposures, although the temporal span could be larger than the 5 years that DES took. So probably the rest of the southern hemisphere is going to be very inhomogeneous in what we're able to give you as far as parallax and proper motion. Okay. Just as an example of what happens with this, this is looking at the Sculptor dwarf spheroidal, which is sits inside the DES footprint. And the green stars are the ones that Vernon is now able to determine as probable members of that of the dwarf spheroidal by proper motion. And you can see that it follows the main sequence several magnitudes down below what Gaia can do. Right. Here's a prediction from Daniel about the benefit of this turbulence correction alone on LSST versus without any DECam. Okay, so the red line is what his simulations suggested would be obtained for proper motion uncertainties, milliarc seconds per year, versus magnitude from 10-year LSST data. And then if we can do the turbulence corrections to 3 milliarc seconds, we get down to the green line. Okay. So you can see, of course, that the gain is largest where the turbulence is dominant over the shot noise of the star. And you see less impact when you're getting here close to 24th magnitude, where the shot noise from the background is contributing a noise that's comparable to or larger to the turbulence. Okay, so the status is of this project is that essentially all the DECam data have been reprocessed to catalogs, all the useful DECam data. And for DES, we've done the static and turbulence solutions and a first round of 5-parameter fitting. We are in the process of extending this DECam characterization from the end of 2019, the start of 2019 when DES ended, through to basically today, so that we can do the precision astrometry on all those, an extra 160,000 exposures. So we are ready to run the code on all those when it's done. Vernon is still tweaking some of the high proper motion algorithms, but this is in process. And these algorithms are running on Rubin images, but there's still plenty of experimenting to do to learn what the characteristics of that instrument are and the best way to fit them and everything like that. So we're looking to have the DECam catalog, I would say, in this calendar year. And then it will be ready as soon as, I don't think LSST is going to have their data ready to combine with it in this year, but maybe in early 2027. I don't know the schedule exactly. I just have a few figures here that Pierre-Francois sent me or showed us. This is the X and Y components of atmospheric turbulence as measured on some early Rubin exposures. Right? And red to green, as you can see, is plus or minus 30 milliarc seconds. So it's substantial, and it has this streaky pattern that we've seen with other instruments. And these are the correlation functions, 2-point correlation functions of that turbulence field in E mode and B mode. And if you're not a cosmologist, you may not speak E and B mode, but these are this is basically showing that it's curl free, that it's all in this E mode. Okay. And the amplitude is about 800 milliarc seconds squared, or as we said in RMS, around the square root of that, or 30 milliarc seconds, right? Okay, then this is the model that Pierre-Francois made using the Gaussian processes, and these are the residuals to that model. And you can see that that correlation function is now essentially 0 on this scale, right? But this is a coarse scale, so it could still be there at a few milliarc seconds, right? So it works, and we have some better algorithms that he's testing out now. And then these are the residuals after Claire's best instrument model and Pierre-Francois' best stochastic model have been subtracted. And you can see an interesting pattern of residuals here that this is averaged over many visits, a few thousand exposures from LSST. And those of you in the know that there are two different kinds of CCDs in the focal plane. And you can see that one of the kinds of CCDs has they have two very different characteristic patterns of residuals. And this is what that pattern looks like if you take its divergence and its curl. And that's what the connector on the back of those CCDs looks like. Okay, so they're really making rapid progress with the data from LSST in figuring out what all these little milliarcs, a few milliarc second, 10 milliarc second tweaks should be for that instrument. Okay, so that's what I wanted to show you. Here are references to a few papers that describe the things that I showed you, at least the ones that have already made it into papers. The Rubin stuff is new, right? That's not published anywhere. That's a courtesy of Pierre-Francois to leak that out of the Rubin project to us. Yeah. Yeah, that's what I wanted to let you know about, and interested to find out what you guys would be looking for in this data and whatever questions you have.
Well, maybe people could raise their hands if they have questions, and then we can call on them. And maybe I'll just go ahead while we're waiting. In terms of your catalog and the dark energy only results, you could imagine that there are faint stars that are, dropouts in, say, G band because they're very red and so forth. Will those still get processed through? Uh, are there
Yes.
EY only things, that kind of thing?
Right. So this is, of course, one of the motivating science things is of the high proper motion part is to look for brown dwarfs or isolated neutron stars, that would be extremely blue instead of extremely red.
Mhm.
So we have no requirement that you find it in all the filters, right? But you do, between the filters, have to find it enough times that you can fit it, right? And also not be lost in the confusion of random things that happen to connect
Mhm.
into a nice moving pattern, right? So we don't know exactly how many apparitions we're going to need to get rid of the false positives.
Yeah.
But we are definitely, we did say, okay, we're not going to do the wideband data. And so, I guess if we were looking for brown dwarfs, we might do better with that. But you guys are the experts, so I'll ask you the question. Can DES find anything that isn't already known from WISE as far as brown dwarfs?
Well, I think the answer is yes. It all depends on the sort of temperature range that you're competitive in, right? So
Mm-hmm.
that's the warmer things uh, that presumably LSST really clean or dark energy cleans up in. And I
Okay.
think that's been demonstrated like with color only selections uh, in the past.
Mm-hmm.
Now, in
Okay.
terms of, it has 5 arcseconds a year, probably it's also in Wise. I imagine that, I don't know where the trade-off is in terms of motion, but
You mean because it's close enough to be
yeah, I
bright
mean,
enough to
like
be
if
in
you want to,
Wise?
put it to have, Barnard star motion, then probably
Yeah.
it's every catalog, but every algorithm failed or something like that is,
Yeah.
I guess you'd have to hypothesize.
Okay. Yeah.
Um,
So the
yeah,
the
do we
short
have,
answer is we are trying to be color agnostic to the greatest
yeah.
extent possible.
I was excited to see how well the turbulence modeling worked in the leaked. Uh,
Yeah. Yeah. So at this point, we've seen very similar behavior uh, in what the turbulence looks like. We've People have looked at it in Hyper Supreme Cam on the Blanco with DECam, and also with CFH, and now with Rubin, and so we do feel like this seems to be the way the atmosphere acts. Yeah. Was there a
we have
chat
a
question?
question in the chat from Monet about the slides. I would like to post this recording if it's okay. And
Yeah, I can send you the slides to John to go up somewhere too. Pierre Francois is okay with us putting these pictures up. The Rubin police will not come after him.
excellent. Other questions?
Yeah, Tom.
Yeah, I wanted to go to second order and talk about covariances of the best solutions, which is what matters to us in terms of our particular in-kind contribution to Rubin involves probabilistic cross-matching. So you have the positions of your objects in your two data sets, and to zeroth order, again, the idea is you assume that the best fit position is drawn from the truth by some Gaussian with
Mm-hmm.
the measured covariance of the positions. But essentially, what we're seeing in early Rubin data is that the scatter in measured positions doesn't necessarily correlate with the covariance that they are quoting. So I was wondering if you'd done any tests on DECam data on these data, and had
Yeah.
seen
Uh,
whether you were seeing good fits or good agreement between those on your end.
so are you talking about a temporal covariance, like between different measures of the same star's position, or are you talking about a uh, spatial covariance that the errors between nearby stars are correlated?
If you think of it as you've got a square degree of sky, you get a pure sample of matches, nearest neighbor matches is simple as long as they're symmetric and they agree each other's nearest neighbor, like sort of most of your false positives.
Like matching to
You then
Gaia or
take
something?
yeah,
Okay.
Gaia Rubin's exactly what we've done, Gaia DP1.
Okay.
You take the standard deviation of the distances between those objects, and you compare that for sources of the same magnitude, signal to noise. You make them the same star as much as possible. You compare the standard deviation of the distance separation residuals to the quoted covariance of that set of stars, and you would hope that they were the same, or more accurately, for probabilistic cross-matching, you require that those be the same for your hypotheses of match probabilities to make sense.
Yeah. And are
And
these the
we're not seeing those lie on a nice y equals x
and
when we plot
this
those
is
up.
the covariance that comes out of the astrometric of
Yeah,
the
of their
source
pipeline.
extraction.
Yeah.
Okay. So it could be that that covariance only covers the image noise, right? Only propagates image noise. And so that there are either, well, it would be unlikely, I think, at this point that they would be including the turbulence term
Mhm.
uh,
Yes,
in
the one thing
their.
we checked for bright end systematics makes sense, and we checked they had some operations rehearsal data that simulations they ran,
Yeah.
And for the source tables, the single visits, that was what we saw, was that there
Hmm.
was this line comes down and then it just plateaus. And yeah, you say of about order 5 milliarc seconds. Yeah,
Yeah.
that's exactly what you expect to see.
Right.
Um, it was in their co-added images that we were seeing slightly more odd trends.
Uh,
Um, but I guess at that point, it's a question of, is it something they're doing somewhere? It's actually, I'm trying to use you to break my degeneracy. And I would be interested to do the comparison to
yeah.
see if I can pin down where these
Right. I mean,
this is being introduced. Yeah.
uh, the co-adding process is a complication
Mhm.
because it is in some, it should be averaging down turbulence, right?
And your
Um,
catalogs you're providing are only, I say only, will be essentially Rubin source table analyses. You won't be
well,
doing a deep stack, no proper motion.
we will be providing uh, the DECam 5 parameter solutions,
Mhm.
and they're
Which
full
is equivalent
covariance
to, yeah,
tables.
that's Rubin
And
source.
then, right, and then within Rubin, and I don't know what part of the, science collaborations or Rubin project this is supposed to happen, but then whoever is doing the proper motion fitting, right, for Rubin should have access to that information that we produce so that they can have a long baseline to start with. But I will say that those spatial correlation functions on single exposures, that is what we measure, right? We do the Gaia DECam match, we get the residuals, we measure the spatial correlation function of that error because that is the kernel for the
Mhm.
Gaussian process, if you know how Gaussian processes work. Yeah. So, and by the time Pierre Francois has his stuff running and put into some pipeline, it should be the case that you would get uh, that information, right, from them. Now, the one thing that I will throw in, that may be related to your question, is that when we do this turbulence correction, right, the residuals will have spatial correlations as well, right? So when you're doing your fitting of proper motions or parallaxes, this is probably not an issue for your group's science, but there will be correlations in the errors between of proper motion between nearby stars, right? They won't be independent. I guess your stars are generally fairly well scattered, as opposed to somebody who's looking at a distant dwarf galaxy. But yeah,
Well, looking forward to it.
yeah, yeah, Trent.
Trent?
Yeah, yeah. It's really interesting stuff. On kind of related to that, what you're talking about errors and things. Um, I don't think you mentioned like having an error model. So do you have an error model for an individual detection? Because with space telescopes, instrumental magnitude, it would be tied to the astrometric error pretty closely, but then you have to worry about seeing and
Mm-hmm.
um, do you employ an error model? Science-wise, the reason why I ask is because with a good error model, then you can identify astrometrically noisy stars, which would be interesting for binary science and that sort of thing.
Yeah, so when I did the DCAM, so the DES solutions, we we do have. I mean, this is comes out of S extractor, right? Uh, it'll give you a covariance matrix for the X win image, Y win image. So we do propagate those measurement uncertainties all the way through these solutions. And in fact, in doing some of the solutions, we add the extra terms that we know the amplitude of the turbulence on a given thing. What we're not producing right now for you are estimates of the correlations of the residuals after we've done the uh, the turbulence correction. Right. That's something we haven't worked out. We will know on average how big they are for a whole exposure, but it might be hard for us. It slows down the GP a lot
Okay.
to try to get the covariances on the individual residuals.
Would it be from what you provide, would it be possible to compute something like an RUWE type metric or
Yeah, I think so. Right.
okay,
Yeah,
cool.
for sure. we'll definitely be providing. Well, if Rubin does the same thing as we're doing with DECam, you will have an estimate of most of the uncertainty on a given star. Yeah.
Cool.
I do have one question for you all, since I happen to have all the experts here. When we are doing our high proper motion search, should we expect the things that are real to be isotropic? Is that the case for things that are high proper motion because they're in the solar neighborhood?
Isotropic on the sky, you mean?
Yeah.
Like in terms of RA and DEC, like the,
Right.
I think so.
Not the motions, Adam says.
Yeah, not the motions.
Is there a galactic preference to be along the galactic plane? Is that what we would be seeing?
I mean,
Oh, a negative. Okay, a displacement. Yeah. Even for the high proper motion part?
I think there's still asymmetric drift and all of that.
we also don't people proper motions are not corrected for local standard of rest either, right? So there's is that right?
We don't do that.
Yeah, so I mean there would be some the amplitude would vary depending on part of the
Yeah.
sky.
But the things that are moving fast is
But the
generally
PAs, the PAs of things. That's interesting, what Adam says.
okay. Yeah, I was just wondering, how much debugging we can do by looking for anisotropies in the, or use anisotropies to find to separate the junk detections from the real ones. Okay. So aside from local standard of rest, or this, I get what's it called, asymmetric drift, or is that the right word for this V offset?
Yeah, I mean, like the very high motion objects, will be, have preferred directions in terms of their galactic orbits, right? And so presumably that
Okay,
prints
relative to
itself,
the sun.
right?
Yeah.
Or put another way, I think that emerged in the data before anyone understood it, right? And so, like that's why they have weird names like that aren't linked to physics because I think they might be obvious signals.
Okay. Okay.
Okay, do we have any other questions?
Yeah, if anybody has anything interesting to ask or add to what we're doing, please get in contact with me or Alex. We'd love to hear about things that we could do to make this useful.
All right. Well, I think that is our entire agenda for the day. So, if anyone has a suggestion for a topic for a future meeting, sort of just shoot it to me or shoot it to the whole group, and we'll move along. But hopefully, we'll have a meeting, late February, something like that.
Okay. Well,
Thank you so much, Gary.
you're very welcome. Bye.
Did I hear a voice? I guess not.